I recognize most of you, but I apologize in advance if I sort of go over either your project or something that you're interested in too quickly. You can catch us afterwards. We have lots of papers on the website. We'll be happy to talk to people or give them demos of any of this stuff. So first of all, I'll put up the names of everybody. I realized I made a cut and paste error. The newest member of the group is actually on the slide with the wrong name, and I'll leave it for you to guess which person is named incorrectly. But Rustin just joined us this week.
That's not your new cloning software?
Yeah, it is cloning. It's what happens if you do cloning thoughtlessly. So the question that our group has been trying to answer is, can languages and tools help produce better software? And by better software, we don't mean smaller software. We don't mean sort of more functional software. We mean more reliable software, software that has fewer errors in it and is less likely to fail when you use it. And so if you think about our research as I go over it, that's the fundamental question that most of it has been addressing. The approach that we've taken is pretty well summed up on this slide. The basic idea is that redundancy is a good thing, in the sense that redundancy helps expose inconsistency in there. So, and inconsistencies can sometimes point to errors in programs or English text as well. So a lot of what we've been trying to do is to compare what a programmer should be doing against what the actual code is, what the programmer is actually doing. And the way in which we're trying to detect this is by having the programmer give us partial specifications of what some piece of code is actually supposed to do, and then we build tools to compare the actual code against the specification of what it's supposed to do. In that sense, the redundancy comes in because the specification states yet again what the code code's behavior is supposed to be. Our specifications, probably to distinguish it a lot from what Yuri's group has done, for instance, are what we call lightweight specifications. We're interested in aspects of the program's behavior. We're only interested in little pieces. We're not trying to capture the entire semantics of a program's behavior. We're trying to find particularly important parts of the program behavior, things that can be written down quite easily, and also aspects of the behavior that we can check automatically by building tools. So even if you took all the specifications that somebody could write with our tools and put them all together and check them against the program, they wouldn't guarantee total correctness. That's not the goal that we're looking for. We're instead looking for this as a tool to find errors in the code rather than it's a tool to guarantee you that you get perfectly correct software. Another sort of key point is that the programmers provide the specifications. We think that this is important, that there isn't another class of people out there writing the specifications for the code. And the reason for this is the kind of things we need specified are extremely detailed and very closely related to the code itself. And so the programmers are the logical people to write this down. I don't think anybody else has that kind of detailed knowledge. And obviously to make this happen, we're going to have to build tools that reward this additional effort. Programmers are going to have to do something else. They're going to have to write these specifications. And so we need to give them back something. And what we're going to give back is these tools that systematically and mechanically find errors in the code. And the analogy that I particularly like is this notion of types. And let me sort of cast types in a slightly different way than you may have thought about them before. The idea here is that types are really specifications. They're specifications of the value manipulations that programs perform. But, programmers don't think of them as specifications. They think of them as types. They happily write them. They think of them as actually a good thing. But these are an example of programmers writing lightweight specifications and doing it voluntarily and doing it sort of almost uniformly and being very happy with the end product. And I think there are a couple aspects that are worth emulating here. First of all, the programmers can understand and write down the type declarations to specify their program behavior. It seems like it's a natural part of the language. It fits well. It doesn't require sort of special training in writing specification. The declarations that you add to the code also improve the comprehension of the code itself. I mean, they make it clearer. They help explain things. They help name concepts. And finally, the type checking that's applied to the code is fast. It gets applied every time you compile the code, and it finds errors. And from another point of view, the types serve several roles. They document the interface of syntax in a lot of places. They're a basis for building program abstractions, particularly types in the form of classes. allow you to introduce named entities in your program, which are helpful for structuring the code, and they help you find errors. And there's a whole other thing in terms of performance where types might actually help you generate better code, but that's not the main argument. So what we would like to do is extend this approach, which we see as a very successful result in programming. And the idea here is we would like to check other program properties. We're going to look at languages, both in terms of programming languages and then other languages which are specific to the specifications that express the properties. We're going to build tools that check that the actual code obeys the properties that the programmer spec down. And the goal, as I'll remind you again, is partial correctness. We're not looking to guarantee that your program is going to run forever without errors if it type checks or if it checks in our case. And the key thing here is that we're looking for systematic analyses. We're looking for sound, complete analyses that can flag that there's an absence of errors. It can basically tell you, looks like your code is correct with respect to this particular specification. And this distinguishes it from tools like prefix, which are heuristic, which even if they don't flag an error, there may still be an error in your code. It's nothing against prefix, but that's one aspect of the way it was built that it's never going to be able to get around. And we would like to actually try to be able to make a slightly stronger statement, be able to tell you that there aren't problems in your code as well. So let me give you an overview of where the rest of the talk is going. There are two parts, one of which is what I'm going to call reliable interfaces, and I'll explain what that means in a second. And there are 3 projects there. And then there are 2 other projects which are less advanced and sort of more in the getting going stage, which I'll briefly talk about at the end of the talk. So in terms of these usages, we basically have sort of taken the point of view that interfaces, either interfaces that Microsoft exports to the world as a whole or interfaces within a piece of software itself, have usage rules. The ones that we export to the world as a whole typically have documentation that come in these big, fat, awful books that sort of give you lots of prose telling you what the interface is supposed to do and lots of examples in case you didn't understand the prose. You can just cut and paste and take someone else's working code and use it there. The problem with the specifications in this form are that they're incomplete, they're unenforced, they're wordy, they're hard to follow. You can think of many, many adjectives to describe them. And a lot of these specifications have to do with things like the order in which you apply the operations in the interface, the order in which the data accesses occur, who owns an object so you know when to deallocate it in languages without garbage collection, other types of resource management issues as well. And if you don't obey these rules, the bad behavior can cause your system to crash, deadlock, you can get security problems, blah, 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 blah. Okay, and to give you a concrete example, here's one that we've used a few times before, which is a specification from the socket code. And this is actually the Unix socket code, but the same thing actually applies to the Windows socket code. And you can see it's a fairly sort of boring piece of prose that sort of tries to specify in great detail what it means to create socket streams and all the operations that you have to invoke on them using the interface there. So the projects that we have are actually looking at different points in the space. So let me just sort of try to cast out generally where they are. The 3 axes I have here are precision going that way, scalability, which means sort of the size of the programs we can handle in these tools going that way, and then what I call change, which is sort of the disruption that's going to happen to people writing code currently, or if somebody has a code currently going up. So SLAM is very much focused on this precision. It's not to say that it's not scalable. It's just that the goal in SLAM is to produce the best results possible, the fewest false positives. ESP has taken the direction, looking out in the direction of scalability, with the trade-off being, obviously, that we're going to get less precise results. We're going to probably have more false positives. Vault, I think, is also out on the scalability axis, but because Vault is a new language that involves that you're actually going to have to write things in a different language, it's going to require bigger changes for programmers to adopt it. And I should point out, particularly since I see lots of people in this group who are involved in these things, it's not to scale. I'm a terrible artist. These things probably should have more perspective to them. Okay, so the first one I want to talk about is actually the one that involves the biggest change, which is Vault. And then I'll go back and talk about SLAM and ESP. So the idea of Vault is to take these specifications of the program's behavior and fold them into the language's type system. The idea here is that when you write an interface, as part of writing the interface, you not only write down the syntax of the interface, the calls and the parameters and the types, but you also write down these behavioral rules that say how you're supposed to use the interface. And the compiler, which is compiling a client using the interface, will reject the client if it violates these behavioral rules as well as if it violated a value typing rule. And every violation of the rules is guaranteed to be found, but like many type systems, there are legal programs which wouldn't violate the interface's behavior, which may not type check. So why type-based approach? Well, again, I've made the argument earlier in favor of types, and I think that the idea here is that if we can integrate this type of specification into the actual programming language, it fits very nicely into the type, the types in the programming language, and then the language and the code and the specification are all written in the same syntax. They're all written together as part of the same entity, and it's easy to keep them in sync. In fact, you have to keep them in sync, otherwise you're not going to be able to compile your code anymore. The developers find the bugs very early when they compile their code, and they can fix them before they actually execute the code. The programmers understand the violations because the specifications are part of the language and very close to the actual code itself. And the analysis is incremental and fast, like most type checking. So you can do a single file at a time without having to do a whole program analysis. So let me talk a little bit about some concrete examples. So here is the listen operation from the sockets interface. And this is the way we would write it using the vault notation. So here we have a socket and an integer is listen, returns void. So we've now added some vault annotations. This says this is a track. This socket is a track type, which means that it's a type that vault knows about, and it's associated with this resource S. And then over here, there's a description of what this function does to this resource S. So the S has to come in the state of being named, and when it leaves the listening interface, it's in the state of being of listening. So I'll show you a little bit more about that. So there are two things here. First of all, we introduce these track types as part of the type system, which allow us to give these compile time names called keys to objects there. And these keys can have symbolic state that allow us to model the state of the object that they're tracking. And this allows us to write down these rules that are static in the program. So let me just put all this down. So there are a couple things you can do with these track types. First of all, we can say that in the case of socket, what we're going to do is we're going to actually create a new socket. So we have to create a new key to go with that socket. And so we say here we get back a new S, just in this track type over there, and it comes out to state raw. Obviously, we need to be able to consume these keys. So for instance, when we close the socket, we need to be able to say that this key no longer exists in the program itself. And we need to be able to change the state of the socket. So here, when you do a binding, it goes from raw to a named state. And so this allows us to write down these state machine-like transitions that describe the behavior of this particular object that's being tracked in the program. And tracked actually is a compile time notion. It's not a runtime notion in this case. So here's what we would do to decorate the sockets interface right there. All the stuff in yellow is the code that we would add in a vault-like behavior. I'm not going to sort of step through it all, but you can see that it's not a huge change to the interface. And if you actually look at it, it all makes a great deal of sense in terms of sort of exactly what the functions are doing with respect to the socket that they're manipulating. Okay, so what happens? So the way the Vault compiler uses this is that at every program, the Vault compiler computes the set of keys that the program holds at that point. And this is a compile time notion. And we look at the set of keys that are created by functions. We look at the set of keys that are affected by invocations of other functions. And there are a couple other sort of rules about how keys. First of all, they aren't leaked by the program. They have to actually be consumed by passing them, for instance, to a close function. So it's not okay to have a socket and just let it disappear because the variable goes out of scope in the program. That would be flagged as an error there. We also check on every path through the function's behavior that the preconditions for a function are met by the set of keys that the program holds. We also check that the operations in terms of memory access and allocation are satisfied. And because this is type checking, because we want this to be fast, as a further condition, we require that when control comes together at a particular point in the program, the set of keys be uniform so that we don't actually have to track different sets of keys along different paths in the program. That would make it extremely expensive, and we wouldn't be able to do the fast type checking that everybody's familiar with. So let me take an example. So here's a piece of code that creates a socket, binds it, listens until it gets a shutdown message. It basically does an accept on the socket, gets back a new socket C over here, does a receive, closes the socket there, then goes back and sees what it gets on the original socket. So this is, you can think of this as sort of a sketch of the way a server would work, say a web server. So this piece of code right now is fine. Notice we added a couple of annotations to it in yellow to sort of correspond to the annotations that are on the interface. So what the compiler would do is it would compute the set of keys that are held at various points in there. And this is the set. They're basically sort of two keys, one of which corresponding to this socket up here, and the other one corresponding to the socket J down, the socket with the key J down there. And you can see that they're there. Yes? Sure.
What if new keys are created inside the loop so that you have kind of growth?
They are, in fact, because this accept call gives us back a new socket which has this key J associated with it. And so J is a static name for the socket, which is a new one of which is created every time we iterate through this loop. So what has to happen, though, is that sort of all of the sockets that are created have to be uniformly dealt with this single static key, J.
Can you track through arrays?
Could you speak a little louder?
Yes, can you track through arrays?
Can we track through arrays? Manuel?
You cannot track the individual elements of an array, no. You track the entire array.
And I think the same caveat applies to data structures. You need to have a single state that applies to all the elements in a data structure, at least all the elements of the same type in a data structure. So let's see what happens if we actually go and change this code and introduce an error into it. So notice down here we're closing the socket we just did the accept on. Suppose we break the code by changing it to close the socket that we opened in the outer loop. It's a real easy mistake to make. I'm sure everybody's done it. So what happens here is we get a different set of keys right here. And there are a couple things wrong with this set of keys. So first of all, at the join point, when we go back in the while loop, the sets of keys are different. So here we had the original key in the listening state. Here we've closed the original key, and this one's actually gone out of scope down here. And so we have a different set of keys. And so the merge point, we're going to actually notice that there's an error there. But there's a bunch of other errors we'll also see. We're leaking the key because basically we opened the socket here and we're not closing it. So there's a resource leak there, which we shouldn't allow. And then finally, there's also a botched precondition down here. We're trying to close something which we closed up there. So we actually have an embarrassment of riches. The real question is sort of which of these errors do we want to report as the error in the program? Yes?
Also has syntax that you can describe error cases. For example, say you can describe that if bind fails, then it's not in a named state.
Manuel,
Yes, this is just a naive form of the interface. An actual interface has many more cases because of the failure possible.
So, sort of step back a little bit, take a look at the Vault resource. The key idea here is that we've added a few features to the programming language to express and check many resource usages. It's still an imperative programming style. It fits into a very C-like language. The Vault language is an intent to sort of give programmers who are familiar with C a language that will be comfortable to them. We've written real applications in it. We've written a device driver which we've loaded into the kernel and run. We've written a fair amount of DirectX code, which uses the DirectX library, which is another complicated library. Can check real rules that developers commonly violate, and it seems to have a fairly natural feel in terms of stating the rules. The ongoing research is to try to take this idea and fit it into a C# framework. So instead of being based on a C-like language, we're trying to see whether we can actually do this on top of C# so that it'll be a little bit more accessible. Yeah?
So you mentioned that if the close is taken out of the inner loop,
Yes.
would cause an error saying that the key is being leaked out of the loop. I didn't quite understand that. You could have a separate loop elsewhere that closes the sockets that were created there, right?
So the particular is that if we change this close, we're closing this socket, and then right here we've created a static a scope variable C, and when we get to the end of its scope, we haven't actually closed it. And so the resource that's associated with it, this key, it just goes out of scope without us actually freeing up the resource.
I mean, you're right. The socket itself is not scoped, of course. I mean, it can live on, but then you have to pass it on. Right. So here you just don't have. There's no code that actually passes it on to the place where it will eventually close it.
Yeah.
So would the compiler notice if I actually did an assignment to something like an array? Or
That'd be fine.
so there'd be no.
Other questions? Okay, so that's the one project Vault. So now, remember, I'm going to shift gears. Now we're going to talk about another project, SLAM, which is, I think, the earliest one that the group got going. And the model for finding errors in SLAM is a little bit different. The idea here is instead of starting with a new language and a program written in a new language, we start with C code as is. So basically the source code from any product that Microsoft has. We have a set of rules to describe an API which are written in a language called Slick, which is a separate entity from the program itself. They're actually sort of, it's not integrated into the type system of C. It's not integrated into the program itself, but they're actually a set of rules there. And we have a collection of tools that go through and check whether the C code meets the specification in the Slick language. And the process that it goes through is we create an abstraction of the C code that discards much of the irrelevant detail, and the abstraction is based on a notion called a Boolean program, which I'll show you in the next couple slides. We then do a systematic exploration of this model of the program's state space, looking for feasible paths that lead to errors that the Slick specification has identified. And if we find these errors in the program, we do a refinement of the model to make sure that we aren't including infeasible paths through the model. And again, I'll sort of show you this in an example. So let's take a real simple specification, real simple state machine. So here's a state machine that describes locking. So you start off in the green state in unlocked. If you do a lock operation, you go to the white state, you're locked. If you do another lock, it's an error. If you unlock, you go back here to the unlocked state. You're not allowed to unlock the unlocked state. Otherwise, you get to the error state. So you can obviously change it to fit your favorite locking protocol. In Slick, it would look something like this. The idea here is that it's a state machine in sort of the classic state machine sense. It's written in C code, so it looks very natural to a programmer writing down this kind of specification. So the question is that if you get a piece of code like this, which is, I think, from one of the Windows 2000 device drivers, and it has the code in yellow, which requires locks. So I know nobody can read it, but this is KE acquire spin lock. Here's a release KE release spin lock. Here's another KE release spin lock. And there's a fair amount of control flow in here. The question is, does this code actually obey the locking protocol on the previous slide? And if not, why not? So the first thing we do is we take the code and actually instrument it with the specification. So the red code here is the lock and unlock that corresponds to the state machine that the programmer wrote down in the Slick specification. And then we just look at the code sort of expanded out, throwing out some of the detail with the ellipses there. So again, we still have this question. We have a while loop, and there's an if in here which calls the unlock. And the question is, do we do two of these unlocks in succession? Do we actually go into the conditional and then fall out of the while loop so that we do two unlocks? It's a good question. I mean, looking at the code, you could probably figure out the answer in a minute or two, but I won't let you do that. So one thing you can do is to basically just do a simple state-based exploration. So we start up here and we're tracking this state machine. It starts off in the green state, which corresponds to unlocked. We do a lock. It goes into the white state. We come down here, and if we fall out of the while loop right away, well, then, we did the unlock. When we got out of the while loop, we end up back in the green state. So we didn't see any errors along that path. So let's track another path. So here's the path where we actually go through the if statement. We do the unlock there. We come out, and we do another unlock, and it's an error. So if we just do path-based tracking without sort of any cognizance about whether the paths are feasible or not, we're going to find this error, which turns out to be actually a false error. So in the SLAM approach, we start off by building a very simple abstraction of the original program in Notion that's called a Boolean program. And we do that by throwing away all the statements that really sort of do anything in the program. So we throw away all the computation, and in fact, we throw away all the predicates in the control flow. And we end up with something like this, which has the structure of the control flow, but no real content to it. And so if we actually look at a pass through this, all the paths are pretty much feasible, and we're going to see the same problem as we saw before. So we've now found a path through this Boolean program that looks like it's an error, but now we're going to ask ourselves the question, is this path actually feasible in the original program? And at that point, we're going to throw some fairly high-powered reasoning at it. We're not going to just sort of do a simple state-based exploration. We're actually going to look at the predicates along the original path and ask ourselves the question, is this actually feasible? And it turns out that this path is not feasible in the original program, and so we're going to refine the model there by introducing a new variable b, this Boolean variable b, which represents the condition n packets old equal n packets. And this is actually the real trick behind SLAM, is to be able to figure out what these Boolean variables are and the conditions they represent so that you can rule out infeasible paths. And so if we add that to here, what we see is basically, here's the code from the original program that has to do with n packets old and n packets in the program. We're going to replace that in the Boolean program with assignments to this Boolean variable and tests on this Boolean variable. So we still maintain not having the actual statements from the original program. We've instead replaced them with this abstraction b. So now we ask ourselves again the question of whether the path through this modified abstraction of the program, this modified Boolean program, is feasible. Yes, Jerry, sorry.
The feasibility check surely is undecidable in general, so you have to do some tricks, right?
Sometimes we're not going to come up with an answer, right? I mean, it's obviously undecidable, and that is one of the possible answers this tool will produce. Is I don't know. It may fail to terminate in some conditions, and unlike many, for instance, compiler tools which want to make the conservative assumption always to avoid that case, I think in this case we're willing to tolerate non-termination as a possible answer.
Well, we've never run into the case where the theorem prover isn't powerful enough, so it implements sort of standard decision procedures for equality, inequality, linear arithmetic, simplex, and it's good enough for drivers so far.
Right, and that may be, maybe a statement about software, and it may be a statement about drivers.
It's not a theoretical statement.
It's not something that we expect to hold true forever.
Doesn't matter, whatever works.
Whatever works. Okay, so here we have our Boolean abstraction, our refined Boolean abstraction. Now we ask ourselves, is this path feasible? And we can trace it through, and there's the first path, which doesn't go through the if statement, and it's fine. And now what we see is that the condition when we leave the if statement is that the variable b is not true, and so we actually iterate back up to the while loop. We don't fall out of the while loop if we've gone through the body of the if statement. And so the original path that we found the error along was infeasible in the program, and so there isn't an error because you couldn't have executed the two unlocks in succession in the code. So the programmer who wrote this in the first place may not have written some beautiful, clear, transparent code, but he did write code that was correct. We were able to show that mechanically. So this is sort of the overview of it. I'm not going to go into all the pieces of SLAM. In a second, I'll give Tom the podium and let him show you a demo of SLAM. But there are a number of tools that we've built up that allow us to extract the Boolean programs, to refine the Boolean programs, to do theorem proving on the paths that we find through the programs to decide whether they're feasible or not. So let me skip that one too. So summary. Automatic program analysis, the key thing here is that there's no annotation of the code. The specifications are written off to the side. In certain domains, this is pretty much essential. So think of device drivers where there are 100,000 device drivers out there. No one's going to annotate even a small fraction of them. But if we can write down the specifications for the API separate from the device drivers, we can check them automatically against the specification. The errors, as you'll see from Tom's demo, are reported at the source level in great detail. There's a very precise analysis which minimizes the false positives that we find. And the current research has been to apply this to the device drivers and to try to make it as scalable as possible. So, Tom, you want to show?
Sure.
Yep, you're there.
Okay. So what we're doing with SLAM now, that we worked out a bunch of the theory and algorithms, is to really specialize it to what we call the static driver verifier. So this is SLAM, really specialized to check properties on device drivers. And if this would cooperate, all right. Well, maybe it won't cooperate. I'll discuss that in a second. Oh, we're running on a remote, so it's probably. Well, is anything going to work? Let's see. Okay, it looks like we do have some interactivity. Okay, now it's decided to respond. Okay, so what I'm going to briefly demo to you is a specialization of the SLAM toolkit to device drivers. The basic idea of SLAM, as Jim said, is to take any C program and any sort of slick specification and to run that. But we want to first make SLAM work very well in device drivers and essentially deliver a standalone tool that has the properties baked in. So the specialization is really in just having a set of properties sort of pre-written by us that are wrapped up with the tool, so that the device driver writer doesn't have to write new properties. They'll just get a tool that will run, and we will have done all the engineering necessary to make that work on most device drivers. So the basic idea is in SLAM then is that we have the SLAM toolkit, and you can forget about the internals. We have these rules, and I'll show you a very high-level description of a more complicated one. And we have some model of the kernel, some C code that essentially represents what the kernel is doing. And the placeholder is going to be the C code for a particular driver. Okay, and so this box is what we're going to be delivering to NT, hopefully sometime next year. And the basic idea is to either say you've got a bug with respect to one of the many rules that we're coding up, or to say with respect to some set of rules, your device driver checks out okay. And of course, the idea is to make this scale to as many drivers as possible, so that this really just becomes another tool in the programmer and tester's toolkit that they can run drivers on and get bugs. Of course, we're going to be able to add new rules, so we can add new rules as things go on. This is just one rule that device driver writers have to follow that has to do with completion of what are called IRPs, I/O request packets, in the driver model. And the basic message to take away here is that this is one small part of what it means to follow the device driver rules, and it's a fairly large state machine. This has to do with synchronous versus asynchronous handling of requests. So the basic idea is at the top is the state machine, which has to do with when you are able to complete the request synchronously, and the lower part has to do with when you are pending the request. Okay, and I'm not going to go into the details, but show you the results of running that spec against some code. So what we do is we take a spec like this, which is a sort of traditional state machine, and we code it up in the syntax that Jim showed you, and then use the SLAM toolkit to check it. Okay, so when we run that specification, we ran it on a floppy device driver in NT, from NT. And in this case, SLAM reported an error and generated a trace. And what we're looking at here is a trace through the source code of that driver that gets us to the error, to an error state in that specification. So the code of the driver is here on the right-hand side, and on the left-hand side is the trace. So we're giving you the illusion of a static debugging session with a full trace through all the procedures that took you right to the error point. And so this is one of the nice parts about doing static analysis, as opposed to sort of what kernel debugging is normally like with a serial connection across, to your debug machine. So here what happens is the device driver, we have a model of the OS. The device driver comes in and does this queue IRP to thread, and we can go in there and see that it does an IO mark IRP pending somewhere here. So down in that code, we're 3 function calls deep, I think, or 2 function calls deep. It basically signifies to it notifies the operating system, I'm going to pen this request. Okay, and then as expected, as we go down in this code, we can see it returns status pending right here, which is what you would expect. If you're marking the ERP pending, then you should return to the operating system that you are pending the request. So that's one of these properties that whenever you call IO mark IRP pending, you have to pen the request. Now the bug comes here. Here now they're calling a lower level driver with IO call driver and taking whatever the result of that is and assigning it to NT status. Well, it turned out in a previous version of the OS this was okay because it would always return status pending, which matched the previous value we wanted to return. But it turns out under a new version, it was possible to get another status code. And so the driver would actually pen the request, call the lower driver, and then return to the kernel a status other than pending, and that's not allowed. Okay, that's a bad thing to do. So the fix here, at least what they told us, was to actually just ignore the return code. There actually is a bug with that as well. But this is essentially sort of the class of error we can track. You have a correlation between sort of a sequence of calls you have to make to the operating system and the return code, and this is one of the many types of errors that we can catch with the SLAM toolkit. Yeah.
So you're showing the paths. This is static analysis.
This is static analysis.
So you're showing the paths for the programmer to see where the
error is.
Are you also giving some kind of conditions?
Yes. So I've ignored that totally. So when we are computing this path, we've basically given it to a theorem prover, you can say, to say, is the path infeasible? And in this case, it said, no, this path is potentially feasible. There's no contradiction. And so at every point in the path, down here we've got some state variables, and these are all the conditions that SLAM had to build up in order to remove the infeasible paths. So it doesn't show you the complete state of the program. It only shows you sort of what it needed to show that you had an error. And we haven't really done a good job in presenting this, so I sort of skip over that. But that's another nice aspect of the output of SLAM. You not only get the trace, but you get the explanations. Here it's fairly low level. At every point you're going to have this set of predicates, and we still have work to do in sort of improving this presentation. Okay, so that's the basic demo, and this is just summarizing what Jim summarized already.
Thanks, Doug.
Okay. I think you're back on 1. Is that right?
Question, how big a program can you handle given the scalability?
The largest we've done so far is 30,000 lines of code. But the scalability is not so much an issue of the number of lines of code. It's really the number of Boolean variables you need in the model. So the basic analysis phase so scalability is not just the issue of number of lines of code. And we expect to be able, in a few months, to be at around 100,000. And there are some drivers that are over 1 million, and we hope to be there someday. But we believe we can reach some of the graphics drivers are really big because of all the protocols.
Unfortunately, by the time we get to 1 million, there'll probably be 2 million.
But by the time we get to 1 million, I think I'm going to have a lot of gray hairs.
Oh, okay. I have to ask, what kind of drivers are 1 million lines?
Yeah, the graphics drivers. So in particular, these have to implement many different interfaces, OpenGL, DirectX, various flavors, and there's just really a huge amount of code. Now that said, I think we could potentially analyze those because a huge amount of that code is not at all concerned with the downward interface, shipping the polygons, right?
Yeah.
Whereas we're concerned with sort of the upward-facing interface to the OS. And if on every polygon sent through you did a complicated interaction with the OS,
It did a state machine.
yeah, right. So that's the reason we think we can even scale it. The state machine is going to sort of filter out a lot of the code, and but still, it is an amazing thing. There are device drivers that that are that large.
And they're getting bigger as we speak. Okay. So let's move on so we can actually finish in a reasonable amount of time. The next project is ESP, which is a project that Manavir has started. And the idea here is to try to push out in another direction, which is in the direction of scalability. So if you think this idea of taking a slick specification and checking it against actual C code or C++ code is a good approach, then you'd like to be able to do this with sort of fairly large pieces of code like, SQL or Office or even NT itself. And you'd like to be able to do this automatically as much as possible. And so that's what the goal is behind ESP, is to head out in the direction of scalability, perhaps at the cost of a little bit of precision. So again, to distinguish us from prefix, the key thing here is that it's a sound analysis. We can actually find all the errors in the program, or even more interestingly, tell you that you don't have any left in your code. So the differences from SLAM are up there, is that there's a slightly less general set of protocols that you can write down, and it's really intended to scale because the analysis is a little less precise. So again, here's the same slide, except for written in a slightly different way. Again, the idea here is that we're going to attach finite state machines to describe data items, to describe the actual behavior of the data items, and then we can trigger the transitions in the state machine using syntactic patterns. So for instance, this table would show the C code that you would do right here, and I think this is taken from SQL, their locking protocol for objects. And here's the transitions in the state machine that correspond to it. So the insight in ESP that makes this all work is that there are really sort of three different things we have to track to watch this happen. One of which is the sequence of actions that occur along a control flow path in the program. Another is the data items involved in the actions. And the example in yellow there shows why you actually have to track the data values, not just the names in the program. So here, we do get on an object, and then we assign the object to another variable P, and then we do a release on P. That's the same object, but it just has a different name. So it's not enough to just track the variables in the program. You actually have to look at the values. And the final one is the one that we made a big deal of in the previous presentation, which is this notion of feasibility. We really do need to be able to throw out infeasible paths, otherwise we're going to have a lot of spurious errors in the program. And the key insight that ESP uses is that we can use different forms of program analysis to track these three different entities in the program. And by choosing the right type of analysis and the right degree of precision, we can get good results and scalability at the same time. So the three phases of the analysis in ESP are: there's a global value flow analysis based on some previous work on a tool we did called Golf that builds the call graph in the program accurately and then does a value flow graph to actually track the way values flow in the program. There's global protocol tracking, which is tracking the state machines for particular values using a data flow like computation. And then there's a final phase, which is within a function looking at the actual feasibility of paths to rule out infeasible paths inside the function. Not infeasible paths across the entire program, but more locally infeasible paths. So this is an example, I think, from the SQL code. And again, this is using get and release for the locks here. And so it's a bottom-up analysis. So what we have here is we have a function. It calls get, and then on some condition it calls this up wake up 0 call, passing in the same spin lock, and then returns. And the question is, do we actually obey the protocol? And down here is the code for up wake up 0, and notice it does a release on its argument. And the analysis in ESP is done on a function-by-function basis in sort of a bottom-up approach. We look at the callees before we analyze the caller. And so we build up an analysis of this up wake up 0, which says release is called on the point, whatever the first parameter is pointing to, and we then do a summary, which basically says whatever comes in as the parameter is locked, and it's going to go to the initialized state. If it was in the initialized state originally, it wasn't locked. In other words, it's an error. So we basically have built up a summary of what this function does with respect to the locking protocol. And that's what we're going to use when we analyze this function up here to see what it does with its arguments. So here, again, we're just basically looking at the way the value flows, and we're going to use the summary that we've created in our earlier analysis to see that the protocol actually is obeyed correctly. So, we got an implementation of ESP. It actually is up and running through some heroic efforts this summer. We've been able to use it to verify a protocol which describes how you use the standard I/O library, the file there, on a 150,000 line program, which is actually GCC. So GCC manipulates 15 different files. It has all sorts of switches that tell you whether to dump output to this particular error trace file or not. And with ESP, we were able to verify that GCC manipulated all of these file descriptors correctly, didn't try to write to file descriptors that weren't open or after it closed them. That's pretty impressive. It was pretty quick on 150,000 lines. There's still a lot of work to be done. It's still a prototype, but working on extending it to the full C++ language, not just C, and to improve its speed. And the key notion behind all of it is that it seems like for many protocol errors, and this is not to say all of them, this type of scalable analysis, this type of scalable program analysis is going to be sufficiently precise. You don't actually need to track a value interprocedurally across all the paths interprocedurally. We'll actually be able to build up these summaries and get back summaries that describe how a function manipulates a value and use these summaries in lieu of tracking all the paths through the summary. And I think the key notion here is that if you make the usage patterns for values way too complicated for us to track, programmers probably can't get them right either. So in other words, if to use your library, I have to understand that there are many different paths through it, all of which have different effects on the values that I'm passing in. It's going to be very hard to use your library call. And so there has to be a fairly simple set of rules to describe how some function is going to be used. Otherwise, programmers aren't really going to get it right either. So Monavir actually is going to come up and give us a demo of ESP, or a prototype version of ESP. Yes?
So does the tool that tell you if the usage pattern is too complicated?
In the form of giving you false positives. So I think that it gives you negative feedback in the sense that it'll flag things as errors that aren't really errors. I mean, I suppose we could easily build in things where we saw very complicated descriptions coming out and reported that as a warning to the user that, maybe you should think about this function because there are paths to it that have very strange behavior compared to the other paths.
I can imagine projects mandating that they obey the complexity limits on
Yeah, I mean, the system is built up in such a way that it releases models for every function. And you can go in, you can look at them, browse them, check with them manually if you want to improve. Sometimes the analysis does a bad job on a particular function that's used a lot. You can go in, tweak that model to make the analysis go better. So yeah, you can definitely improve the kind of stuff you're suggesting. We just don't do it yet. Yeah.
It's an interesting idea. I mean, I guess we're going to have to get more feel for how well the models correspond to what programmers can handle.
Okay, so so this is actually
No one
yeah.
can see you yet.
Oh yeah, nobody can see me yet. Right. Okay, so what I'm going to show you is the output of a run of this tool on part of the SQL code base. And this was actually a run done over the summer. So since then, the analysis has become a lot better and the user interface has become a lot worse. So it doesn't quite reflect the state of the project today. But all of this, because we want to run on Microsoft code bases, is implemented on top of Prefast so that we can run on SQL and NT and those kinds of things, and we use their user interface. So what we did is we checked a very simple property over the SQL code base, which is that in various places you make calls to a get method to lock some object, and then you should do a release before you leave a pretty local scope so that you're not holding the lock too long. And this tool ran over, X million lines of code, and it found 6 errors. And I'll show you exactly what these 6 errors were. And in fact, none of them is a real bug. So we didn't actually find any errors. But the more interesting thing is that this is a complete list, right? And so there aren't any others. So you get some feeling for something that you verified in your code. Okay, so here's the first error. And basically what's going on here is the tool claims that there's a call to get, which is highlighted in red, that is not matched by a call to release. Okay. Now, if you look at the code, what you notice is that the call to get is done under this condition right here. Okay. And then down in this code, there's actually a release that is done under exactly the same condition. Okay. So this is actually not a bug. But the problem here is that the basic analysis is a data flow analysis where we're not tracking feasible paths, and that's why we reported this error. Now, as Jim mentioned in the slides, we have since figured out how to add a level of path feasibility to our analysis. We've run it on a couple 100,000 lines of code. It scales fine, and we're actually pretty optimistic that it will scale to much larger programs. It's a polynomial time path feasibility analysis, but we haven't implemented it for C++, so I can't show it to you running on SQL. Okay, that's the first error. Here's the second one. What's actually happening is that there's a method called lock for this object, which actually is a wrapper on get. Okay, and we don't have any magic, even though our tool is called ESP, we don't have any magic that tells us that this is meant to be a wrapper function, so we go ahead and report an error. We have a specification language, so the way that the programmer would deal with these things over time is that when they get errors for things that are wrapper functions, they'd have to put that into the spec, saying that I don't want to see an error for this function because it's meant to be a wrapper, so move on. Okay. Here's another one. That's another wrapper function. This one is just like the very first error. You do a get under this condition right here, and then down here you do a release under the same condition. Now notice that even though you need path feasibility to track that this is not an error, it's really simple, right? It's the same condition, exactly the same condition being tested. And our experience is that usually people do very simple things with checking these feasible paths. And so we have an analysis that's geared to this idea that we can test very simple things. Here's another locker wrapper, and here's the last example, which is somewhat more interesting. What happens is you do a get unconditionally in the code, okay? And you have this variable frelease spin lock that you initially set to true, which says that at the end of this function, I need to release this lock. But what happens is that under some particular conditions, you end up calling the function upWakeUp0, you pass it the address of the spin lock, and upWakeUp0 actually does the release. Okay, and if you've done the release by calling upWakeUp0, you don't want to do it again because that has other side effects on the system. So what do? If you call upWakeUp0, then you set this other flag to false, which says that now I don't need to do the release. So later on in the code, before actually doing the release, you check the flag. Okay, and once again, this is precisely the kind of thing that we are able to track accurately. And so in the current incarnation of our system, we don't get this error. Okay, and that's it. That's the complete list. And the only really interesting thing about this demo is that when I click next, nothing happens. Right? That's it. These are the errors, and at least for this specification of property that you're interested in, there's no errors in the program.
Thanks, Marvin.
So
Yeah.
why were there no errors? Because prefix found them first?
No, actually the reason we ran this was because when prefix did a run, they weren't finding a whole lot of this kind of error. In fact, for this particular thing, they found no errors. And then the question when you use something like prefix and you find no errors is it because you looked at the wrong paths or is it because there are no errors? Right? And so that's why this is a complementary tool. Now we can say that, you know what, don't bother using prefix to look for this particular error because you're not going to find them. But there may, of course, be many other different kinds of errors that we didn't check with our specification that you do want to use prefix for.
Well, until they write new code.
Until they write new code. But the thing about this tool is it runs pretty fast, so you can have this as part of your regular process. So you just keep running it.
So I think the real answer to your question, Mike, is that those guys are really careful. I mean, it's pretty impressive over 3 million lines that there are no errors in that locking.
Yeah, that was the conclusion of the prefix people after doing a variety of different runs, looking for different properties. They just didn't find a whole lot of errors, and the conclusion was, these guys, they've gone through many versions of the product. They're pretty experienced developers. They know what they're doing, and they usually write code in a way that you can read it and see what's going on.
Okay, let's move on then. So That's the negative 2 bytes. So what I'd like to do briefly is to just touch on the 2 projects in the area that we're just getting started. One of them is concurrency, and the other one is security. So the motivation for concurrency, I don't think I probably actually even need to put it up here, is that, everybody knows that parallel concurrent programs are a lot harder to write, debug, test, modify, you name it, than sequential code. On the other hand, it looks like everybody's going to be writing them in the future because, we're going to have cheap SMPs sitting on our desk. We're going to have .NET out there as a compelling platform to write new applications for, and so there's going to be concurrency, and we're going to have to deal with it. A lot of what we've seen in these different domains are what we call asynchronous programming, which you can think of as message passing, non-RPC programming. Basically, you go off and you ask for tasks to be done, and you run concurrently with the execution of the task. And then at some point later, you somehow rendezvous to get a result back. If you want to look for examples of it, you can look just at the way people write currently using TCP/IP. But if you look at the Hailstorm or the Indigo platforms that people are doing, or another domain, the BizTalk platform, which is for sort of larger grain interactions, they all fit into this model. And so what we've been trying to think of is ways in which to support asynchronous programming inside a programming language as a first-class operation. And part of what we've been trying to do is to fit it into this behavioral model. We would like to be able to write down behavioral descriptions of your asynchronous programs and to check that the code actually meets what you said it was supposed to do. And some of the properties we would like to be able to check are things like deadlock freedom, communication progress. We'd like to make sure that your messages are sent to somebody who can potentially understand them. And currently, there are very few, if any, tools in this domain. It's not like we can point to prefix and say, there's a great tool that everybody's using, but it doesn't quite do enough. And here, we're saying there really isn't anything out there that helps you check these properties. So the project started off being called Behave. We're now designing a language based on the ideas that came out of the Behave project. The language is called Sharpie. And the Behave is a type system for concurrent properties of programs, and it's fairly independent of the language. Sharpie is an extension to C# that actually is trying to take this type system, graft it on top of C#, add some support for asynchronous programming constructs as well, and be able to automatically check whether a program meets its behavioral specification. So, give you an example, and apologize for the syntax. I'll point out exactly what's going on here, and hopefully people can understand it. We will clean up the syntax before we release it to the world. So the idea here is we have a client and a server. Communications across this asynchronous program is expressed using channels, which are these CH objects that have either an in or an out direction here. So the client gets a channel in the in direction, which in other words is a pipe into the client, and it can produce results on its out channel. And the specification over here says that the first thing the client does is it does a receive, which is this question mark on its in channel, and then it'll send it something on its out channel, which is the bang on the channel W right there. So this is a behavioral description of what the client looks like to some other entity that's communicating with it. In other words, there are 2 channels, one channel into it and one channel out of it. And from the outside world, all you see is that the client's expecting to get something on its input channel and then send something on its output channel. So here we have a server. Again, it has some input and output channel, and it has a specification. It's going to wait for something on its input channel and send something on its output channel. And so down here, inside the body of the server, we actually have some code. So we wait for some input on the input channel to the server. When we get it, we go into the body of this select statement right here, and this is an asynchronous call. This is the asynchronous keyword. Here are the channels C and D, which we create for this call, which we pass off to the client right here. These channels C and D are statically scoped, so within the scope of this asynchronous call, we can access the C and D. That's actually sort of key to being able to do the type checking. And so down here, we do a select. We wait for input on D, and then send some output to this channel Y. There are no values here, just to make the example a little simpler. So we're just sort of doing the operations without actually passing anything. So can anybody see what's wrong with this? This actually has an error in it. What? Yeah, exactly. Where basically we have a client here who's expecting to get some input before it produces the output, and we aren't sending anything to it. I'm surprised that you two guys didn't get it. Yeah.
Intuitively, what is channel? If you exchange messages between different sites, what is a channel?
You can think of it as being an abstraction of something like a TCP connection, if that's what you're using for underlying communication, or if you're using a message queue, it's an abstraction of a message queue, or whatever the communication mechanism is. I think we would like to sort of push it so we don't actually have to separate the input and the output channel, so that there would be one entity for communication, like a TCP connection. But for right now, we name them separately, so we can talk about them that way. So in the type checking, what we would see is that, we have a receive and then a send. We do an asynchronous call on the same client, and we do a receive before we do the send. And so if we actually did the type checking algorithm, which we built into the behave, it would detect this error, and it would point out to us that we're not meeting the specification of the client there. So that's the basic idea here, is that we have a behavioral specification, which we're going to fit on top of a message passing-like model of the world, and be able to check the communication behavior, the externally visible behavior of the program. So here, deadlock. Okay, so the other one is just sort of something that we're thinking about getting started. So the idea here is that we have built a fair number of tools for doing program analysis. And the idea is that we could exploit these tools to find many types of errors in programs, security errors in programs. So in particular, there's a class of errors based on information flow. So for instance, here, you might have user input coming in on some variable S1, and then a call to a kernel passing off his value in V. And the question you might want to ask is there actually an information flow in this program such that whatever the user gives me is passed off to the kernel, so that if some malicious user found out about this, they could pass bad values into the kernel. And there are plenty of examples of exploits where people do this in sort of ways that you sort of wonder what's going on. But there are information flows. When people find them, they use them to crash servers. They use them to cause resource exhaustion in servers and so forth. And this is the type of question that value flow analysis is very good at answering. It basically answers the question, is a value that gets here, where does it come from? Or the value that starts here, where does it go to in the program? We can answer this question. We can do it interprocedurally, and we do it very accurately and inexpensively.
Would you also use this type of analysis to check unsafe pointers, things like that? So pointer values into user space as opposed to pointer values into kernel space, where you have to validate that the memory is actually there for the
So you're asking about the user kernel mode pointers? Yeah, I think you could actually use it to do exactly that too, is that you could see the pointers coming into the kernel from the user space, and you could track where they went. And you could ask the question, is along all these paths, do you actually do whatever the appropriate test is the kernel does? We could see that.
You would need some way to seed the thing. Like you would need to know what are the entry functions and which parameters of the entry functions are the bad ones. Or you could use techniques like Dawson Angler's people at Stanford have a set of techniques to try to find the user level pointers, and then you can track those using information.
Yeah.
How would you suggest seeding it?
I think for starters, the way you seed it is just by the entry points to the kernel code. And you mark, you give a specification saying for this function, the fifth parameter could be a pointer to user space. And that's the seed, and then you track where that flows through the code and how it's used.
Gary?
I have a question, maybe too naive. What exactly is value flow? Suppose I have 7, I decrement, it becomes 6, I increment, it becomes 7. It's still the same value, or it's a new value?
No, so that's not quite what we mean by value flow. By value flow, we mean that within the program itself, there are names, the variables that hold values.
I see. It's all symbolic.
Yeah. Right. At that level, it's all symbolic. But at different points in the execution of the program, there are different values in the variable, and they may be assigned into other data structures, into other variables. And so, for instance, if the value that came from the user input, we would like to see where it actually went through the program as it got passed through assignments in the program. So that's more what we mean by value flow. Okay. So Golf is a project which we have actually building on in terms of number of the tools we have. It's a scalable, whole program value flow analysis engine. It does a conservative analysis, so it can handle large programs, and it can also do very accurate analysis that gives you back good results. And so we think that we can actually use this to build on this platform to do a fair number of security tools. So let me just sum up. The approach that we've taken throughout all of this is to look at having the programmer or even the tester write these partial specifications, and the tools ensure that the code meets the specifications. So that's the sort of two key aspects: partial specifications and codes to check, and tools to check the code against the specifications. So if you want to sort of have the pithy summaries, SLAM is extremely precise analysis. ESP is looking for scalability. Vault is an attempt to integrate the ideas into a programming language and make it a sort of not a separate tool, but actually a day-to-day tool for the programmer. Behave is looking at concurrency, and Golf is looking at value flow. And the usual question at this point is like, why do you need all of these projects? And the answer is, I think that they're all looking at different aspects of the program behavior. They're all looking at little tiny pieces of correctness. And so it makes sense to look at that from many different angles and many different scales and build a variety of different tools that can help push us towards the direction of correctness, but never really get us there. Other questions? Okay, well, thank you.